Hi, it's Jason Gorman here from Codemanship with a special one-off charity screencast in aid of the Bletchley Park Trust called Beyond Test-Driven Development. Before we begin, I'd like to say a big thank you to you for donating to the Trust and helping to release this screencast. I'd also like to thank everyone who came on the course on the 21st of April. Between them they raised £3,500 for the Trust, and I know that money will be put to very good use. So a big thank you to all of you. The contents of this course are aimed at people who have perhaps been doing test-driven development for a while, but occasionally find that they need to go beyond test-driven development to produce code that is even more reliable than we tend to be able to achieve using TDD or techniques like that. So over the years, there's a number of techniques that I've used that are pretty pragmatic. There's no formal methods or Z or any of that stuff. And can be applied by most developers on most projects to code that is especially critical. And we'll finish the course by talking about how we identify that code that is particularly critical so that we can prioritize and focus our testing efforts. The techniques I'm going to be covering in this course are mutation testing, which is a technique for testing your tests, a parameterized testing, which is a technique for achieving high test coverage without necessarily writing a lot more test code. Design by contract, which introduces the concept of program correctness and then talks about how we ensure that the interactions between objects are correct. And then we're going to look at a technique called guided inspections, which is an inspection technique that is guided by tests or examples. We're going to look at some test analysis techniques for spotting missing test cases. And then finally we're going to have a discussion about how we analyze the risk that certain parts of our code might present so that we can prioritize our testing efforts. Okay, so if you'd like to have a go at the examples and you're a Java developer, then please download this zip file. You'll find some sample code in there. You'll also find a copy of these slides as a PDF, so even if you're not a Java developer, this is where you can get hold of the slides. So this first screencast is all about mutation testing. So what's all that about then? Well, bugs can hide in the gaps in our tests. For example, if we write a test that just requires that an email address is a valid string, then I can think of lots of strings, valid strings that are not valid email addresses. We could strengthen that test by requiring that at the very least it contains the @ character. So we reduce, we close the gap in which those invalid email addresses can hide. So mutation testing is all about finding these gaps in our tests and making sure that our tests are asking the right questions. It's a method of software testing which involves modifying the source code of a program or bytecode in a small way and then running our tests. A test suite which doesn't detect and reject the mutated code is considered defective. How does it work? Well, we take a copy of our source code or our bytecode and we apply a single mutation operator to it. For example, we might change an AND into an OR. And then we run the test. We run our test suite. If our tests fail, then we say that the test suite has killed the mutant, so it's been successful in that case. On the other hand, if none of the tests fail and the mutant survives, then the tests need to be strengthened potentially. So we would revisit the tests and look to see whether we could make them stronger or better in some way. Examples of mutation operators that we can apply to our code to produce mutants are: we can replace a Boolean operator like an AND with an OR, we can replace a comparison operator like a greater than with a less than, and so on. So there's a subset of mutation operators that we can apply. There are automated mutation testing tools, you'll be delighted to hear, that take all of the donkey work out of this, and they tend to have quite comprehensive libraries of or catalogues of mutation operators that they can apply. So this is just a small subset of the kind of operators we could apply, which I'll be using in this example. I've written some code with some tests for a Fibonacci sequence generator. You ask it for a sequence of Fibonacci numbers of a specified length. The length has to be greater 8 or more, or 50 or less. So no less than 8, no more than 50. Otherwise it will just return a Fibonacci sequence of the length requested. And now I'm interested to know how good the tests are for this Fibonacci generator, so I can use mutation testing to look for gaps in the tests. For example, starting at the beginning here, I see a comparison operator that I can replace. I can make that less than into a greater than, and this is now a mutant version of our code. I run our test suite, and we see that our test suite kills the mutant. It detects the change. Change it back, and then rerun the test just to make sure. Good. Here's another opportunity to apply a mutation operator. We can replace a conditional operator there. Run our test suite, and our test suite kills that mutant as well. So far our test suite looking successful. How about this one here? Let's change this greater than into greater than or equals to 50. So we change the meaning of that expression. And we run our tests, and that they should kill this mutant as well. But they don't. All the tests pass. So there may be a gap in our tests. We need to take a look now. Make sure it's not a false positive. I should warn you, with automated mutation testing, you do tend to get false positives. So be warned. Okay, so what I'm seeing here is that we're actually not testing at that boundary. We're testing for sequence lengths that are less than 8, but not greater than 50. I think I can close the gap in our test by writing 2 new tests. So let's do a test for a sequence of length 50. And I'm actually going to test either side of this boundary, since the behaviors are different. So this kind of defines with the tests where the boundary is and closes the gap even further. So we're going to add another test for a sequence of length 51 that checks that we get the exception thrown that we're expecting, which in this case is an illegal argument exception. So okay, so if we try to request a sequence of length 51, I should say 51, and I can see I've made a little mistake there. I'm checking the sequence length, not comparing it to the actual sequence itself. So now when I run my tests, hopefully they will kill the mutant. And the test that we expect to fail, the one at 50, does fail. So I'm happy with that, and we can revert our code. I've deleted something there. We can revert our code back to the way it was, rerun our tests, and all is well. So we've closed a gap in the test there. Now, I could go through the code one line at a time looking for opportunities to apply mutation operators, but for the purposes of this demonstration, and so as not to bore you to death, I'm going to jump forward. I'm going to skip to a part of the code that I happen to know there is a problem with. There's actually a bug in this code, and this is one of the ways in which mutation testing, as well as closing the gaps in our tests, can help us to detect bugs. So if I mutate this arithmetical operator from a plus to a minus, which is definitely not the right way to calculate Fibonacci numbers, and run our tests, we see that all our tests pass, giving me a strong indication that we're not really testing this particular part of the code. So I'm going to strengthen the tests. What I notice is that we actually only test Fibonacci values for the first 2 numbers in the sequence. I think by testing the 3rd number in the sequence, we may close a gap in the test, but also I have a feeling we're going to detect a bug. So let's do that. 3rd Fibonacci number is also 1. So let's assert that. So we're always asking for a sequence of length 10 and then asking what the third one in that sequence is. It's a 0-based array. Okay, so this hopefully will kill the mutant, and it does. Expected 1 but was 2. And now when I actually revert the code to what it was before and run our tests, if there was no bug in the code at this point, we would expect the tests to pass. But they don't. They fail because it's actually returning the wrong number. The reason for that is that we've got the wrong check here. This tells us that any number after the third number should be calculated in this way, but it's actually any number after the second number in the sequence should be calculated this way. So we could fix it by either making that 1 or making that greater than or equal to 2. And now we run our tests. They should all pass. So mutation testing in this instance has helped us to identify a bug in the code, as well as closing a gap in the tests. So that's mutation testing. As I mentioned earlier, there are automated tools for testing. If you're a Java developer, there are 2 in particular I recommend. One is called MuJava, and there's an Eclipse plugin for that, nice and friendly to use, called MuClipse. Another tool written by our very own Ivan Moore is called Jester. That doesn't have an Eclipse plugin that I'm aware of. That may have changed. You'd have to email Ivan and ask him. But they're both pretty good tools. I should warn you that mutation testing, when it's automated, can be, one, very time consuming. This is a fairly heavyweight piece of computing, so don't expect to run your mutation tests every 5 minutes. But also they do tend to throw up a lot of false positives. So you do need to be mindful of the fact that you'll be spending quite a lot of your time looking at problems that aren't really problems. Having said that, I have found that on critical code it is a worthwhile exercise to run mutation tests on a regular basis, for example overnight or once a week or so on. Now, before we move on to the next screencast, I wanted to finish off by talking about a technique which can achieve similar results but without the very heavyweight approach, and has the advantage of being very much mutation testing in the moment. So you're actually catching problems as they happen and catching gaps in the test as they appear. And that's a technique called adversarial pairing. The way it works is, for a particular requirement or a particular behavior, one partner in the pair writes a test and then hands the keyboard to their partner, who then tries to game the test, essentially to mutation test it there and then. Find a way to pass the test without doing what your partner intended. If you can game the test, you then hand your keyboard back to your partner, and they have to find a way to strengthen the test so that it kills your mutant, so that you can't game it anymore. And you go round in this cycle, gaming the test and strengthening the test until it's not possible to game the test anymore, and then you move on to the next requirement and take it in turns like that. So this can be a very powerful technique of essentially interactive mutation testing, to close the gaps in your tests as they're being written. And I tend to find that this can work just as well as mutation testing, using automated tools later on. So consider adversarial pairing on what you might consider to be important or critical code, but also consider using mutation testing and mutation testing tools on a regular basis, just as a sanity check to make sure that there aren't any gaps in your tests or any obvious gaps. So that's mutation testing. In the next screencast, we'll be looking at parameterized testing.